Welcome back. Lecture at 8. Let's get to transporting gas. So gas transport really depends on pressure gradients and solubility. And so here, what I want to show you folks is a beaker. And this is a partial pressure of oxygen outside of the beaker is 100 millimeters of mercury. And then there's no oxygen in the water. Now, over time, right, we're going to have gases move, bounce, doing, 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 and oxygen, there's going to be some of the oxygen molecules that are going to be able to go inside or be dissolved in the water. So at equilibrium, right? Look at this beaker. And what is this beaker telling you? At equilibrium, do I have some oxygen molecules dissolved in water? Yes, but not that much, is because oxygen is not very soluble in water. It has a little bit of solubility, but it's not very soluble because guess what? Oxygen is a nonpolar molecule, okay? And so that's why at equilibrium, little bit of oxygen can be dissolved in this water solution. Now, let's look at this beaker. This beaker is carbon dioxide. So the carbon dioxide is at the same partial pressure as the example of oxygen, 100 millimeters per mercury. But at equilibrium, how much carbon dioxide is dissolved in the water? Is it exactly the same as outside the beaker? No. And what does that tell you? It tells you that carbon dioxide is not very soluble in water, is because, again, carbon dioxide, is this a polar or non-polar molecule? It is a non-polar molecule, okay? So some non-polar molecules, depending on how non-polar they are, can dissolve or be dissolved in some water in very low quantities. Now what I want you to do is look and compare at the solubility of oxygen and carbon dioxide. Which non-polar molecule is more soluble? Carbon dioxide is, and oxygen is not that much. Now, I want to ask you folks something. Why do we care so much about solubility? And the reason is because oxygen and carbon dioxide are being transported in an aqueous solution, that's our blood. So to counter this low solubility, we have to transport oxygen in hemoglobin. So hemoglobin is an amazing molecule, right? And so it's a protein that has these, what we call heme groups, which is a little protein here that's capturing an iron molecule. And iron can actually chelate, aka pinch oxygen, so it can hold on to oxygen. So each hemoglobin, and the notation for hemoglobin is big H, little g. Each hemoglobin molecule can carry 4 oxygens. Okay, and you don't have to memorize that. It's just, I don't know, some people like to know. Okay, so 4 oxygens. Now, interestingly, what happens is in hemoglobin, there's something called cooperative binding. And man, how this evolved is amazing. So cooperative binding is when you have a molecule, in this case, we're talking about oxygen. When one oxygen binds to this iron, it causes the rest of the binding sites shapes to change shape. That causes it to increase the affinity of hemoglobin for oxygen. Isn't that amazing? Now, that's what cooperative binding is, okay? When one ligand binds, it causes the other areas for ligand binding to increase affinity, okay? And this allows now you to be able to capture more oxygen. Okay, now let's talk about why. Well, one, we use hemoglobin is because, oxygen is not very transportable in an aqueous solution, aka blood, because it's not very soluble in water. And so we use hemoglobin to transport something that is not very soluble, but it also helps us maintain, right? So 1, cooperative binding, hemoglobin. And then 2, carrying oxygen and hemoglobin allows us to maintain gradients, and I'm going to call these pressure gradients, by storing oxygen. Okay, so here, my alveoli, oxygen comes in a little bit, a tiny bit, like I showed you in those beakers, can be dissolved in blood, but only there is oxygen that travels free. However, less than 2%. Okay, majority of it gets transported or taken up in the red blood cells and gets now trapped in hemoglobin. But once I remove it from blood, I've now maintained the pressure gradient. Okay, and then of course hemoglobin will travel, and then this oxygen can travel down its pressure gradient into the tissues that need oxygen. Now I want to talk about a condition called sickle cell. And for sickle cell, some literature calls it sickle cell disease. It can be called sickle cell anemia. And this is a new word. I don't think we, oh no, hello. Did we do blood yet? I'm confused. Anemia is defined by decreased number of red blood cells or hemoglobin. So in a normal cell, right? A normal red blood cell has this donut shape with this biconcave disc. And in here, what I've drawn is these black dots to represent hemoglobin. And what happens if you are in a low oxygen state, nothing happens in a normal cell, is that the hemoglobin stays the same shape and all is fine, except you're in a hypoxic state. Now, the sickle cell, what's happening here is that for a sickle cell, if you're in a low oxygen state, what happens is that these hemoglobins start to line up like this in a chain. And in doing so, it causes now this sickle, right? Shape, right? It's because the cell will now form itself in the shape of that hemoglobin chain. And that's why you get these sickle cells, which one, they have a hard time carrying oxygen in the hemoglobin, and two, you can also now, which is dangerous, in blood vessels, a big blood vessel is fine, but once you start bifurcating your blood vessels, and then the sickle cells are long chains, and they get caught up in each other, and then you can now block blood flow. All right, so now what I want to do is I want to talk about other factors that can affect hemoglobin oxygen binding. So what we're going to cover in the next slides are how temperature affects hemoglobin and oxygen binding, carbon dioxide levels, and therefore pH levels, and then something called 2,3-DPG. All right, so this first graph is something called an oxyhemoglobin saturation curve. So, you folks have been doing saturation curves. This is why I've been training you folks from the beginning of this class to do saturation curves. So I want you folks to press pause and then look at this graph and ask yourself, what is this graph saying? X-axis, Y-axis, and then explain why, okay? All right, so press pause, do it on your own, and then come back. All right, hopefully you press pause. So I always start off with the axes. You folks already know, right? So on the x-axis, it's showing me the partial pressure of oxygen in a resting cell and at the alveoli, okay? And you folks already saw these numbers because I drew these numbers out for you. It took a lot of time to do that, and this is why. Again, you don't have to memorize them, but just be familiar with them. Now, the y-axis is how saturated is the hemoglobin in regards to percent. And what does that even mean? That means how much oxygen is binding to the hemoglobin. Yes? How saturated it is. How are all its sites bound with oxygen? Now, we're going to compare the resting cell and the alveoli. Now look, at the resting cell, about 75, the hemoglobin's about 75% saturated. But at the alveoli, it's about 90, I don't know what number this is, 98% saturated, okay? Explain why. We know at the alveoli, what's happening? What is hemoglobin doing at the alveoli? Picking up oxygen, right? And so that's why it's almost 100% saturated. But as we come down to the tissues, we know that we're going to have now oxygen traveling down its partial pressure gradient into the resting cell, which is why then hemoglobin is not as saturated, is because oxygen is becoming unbound there and entering the cells. All right, now let's look at hemoglobin saturation with temperature. Okay. Now, usually we keep our bodies homeostatically at 37 degrees Celsius. However, there's times where we need to have a fever. And there's times where if, I don't know, don't do this, but if you have hypothermia, this is what's going to happen in regards to your hemoglobin saturation. Now, remember left shift and right shift, okay? So 37 is normal body temperature. If I have a right shift, right? So this is a fever state because look, this is 43 degrees Celsius. What's going to happen is I'm going to decrease. Let me draw the right shift so you folks can see. Right shift, arrow. I'm going to start to decrease affinity for oxygen. What does that mean? That means that hemoglobin is going to more easily be able to release oxygen to the tissues, which is great because if we have a fever, you're using a lot of energy and you're going to need more oxygen. Now, a left shift, right? You increase the affinity for oxygen. And this is the left shift here. Bam. Left shift. So when your body gets very, very, very cold, okay? Very cold, hypothermia, then what happens is that hemoglobin is holding on tight to those oxygen molecules, okay? So that's the effect of temperature on hemoglobin saturation. When you're very, very cold, your hemoglobin is more saturated because it holds on to the oxygen and doesn't let it go very much. But when you're in a fever state, it more readily releases, and so you decrease hemoglobin saturation. All right, so now what I want to do is I want to go over the effect of pH. And I know I went out of order, but pH and CO2 levels are linked. And so in the next slide, I'm going to do both side by side. But what I want to show you folks, again, look at our graph, is I want to show you folks this area where the partial pressure is 40. Because remember, this highlighted area, that's 40 millimeters of mercury. That's that resting cell, okay? Now, in this area, what I want to show you folks is, look at our three lines. We have a blue, a red, and a green, okay? And so here, at pH, so there's 4 scenarios, so I'm going to draw them out for you. First, pH is 7.4, and that's about the normal. It's kind of a little bit high actually, but for our purposes for right now, I'm going to call that normal, okay, until we get into the kidney. But the 7.4 is that normal area, and what we see here is that it's saturated, okay, at 40. Let me draw my line, about 75%, which is what we saw on the previous slide. So 75% hemoglobin saturation. Okay, now let's look at what happens when we become too acidic. pH drops. So pH 7.2, that is acidic. Now what is happening? What happened? What is my saturation? About 60, I don't know, I'm guessing 62% hemoglobin saturation. What happened here? We have decreased our saturation. So what does that mean? That means when we have high acidity in our body, is our hemoglobin is losing affinity for oxygen and starting to release it into the tissues. Okay, now to put this number, let me write that out, right? What these numbers are here. This means when I compare and contrast normal versus acidic, right? This means that hemoglobin molecules release about 13% more oxygen at pH of 7.2 than 7.4. Okay, that's the effect of pH. All right, so let's talk about something called the Bohr effect. And so the Bohr effect is when the shift in the saturation curve results because you change the pH of the body, right? So again, like I said in the previous slide, CO2 and pH are linked. And so the pattern is exactly the same, because you folks already know when you put or dissolve carbon dioxide in water, you're going to make carbonic acid, which releases a hydrogen ion and then decreases pH. So let me explain the Bohr effect. So here, when cells increase their metabolism, right, that's going to lead to an increase of CO2 production. Right? And so when you increase CO2, that is going to lead to a decrease in blood pH. Now, what's happening in response to this increase of metabolism, right, is when and the body evolved this. Man, all these evolutionary changes that the body has done in order to compensate for all of these factors are just amazing. But sorry, I digress. Okay, decrease in blood pH, right? Which means the pH is dropping. I'm becoming more acidic. Okay, when I become more acidic, right, and that acidity now is bathing itself over the hemoglobin. The hemoglobin is going to change shape. The whole course is about changing shape. I'm going to change shape. I'm going to decrease the affinity for oxygen. Okay, this is what we call right shift. And sorry, I should be more clear. Hemoglobin affinity for oxygen. Okay, and in doing so, that will result in an increase of oxygen release at tissues. How amazing is that, people? Bam! Okay, that's the graphs you folks are seeing. I'm not going to rehash these graphs because I already did this graph on the previous slide, because pH and CO2, look at the patterns. Same, okay? All right, let's move on. All right, let's talk about 2,3-BPG. I love this thing. Guarantee going to be on the exam, okay? So 2,3-BPG is a molecule that is made by your red blood cells when you have something called chronic hypoxia, okay? So chronic hypoxia, some examples are if you have anemia. So if you're anemic, you're going to have a hard time having oxygen in the body, okay, for long periods of time. Chronic means long periods of time, not a day, okay, not hours, but I mean weeks, months. That's chronic. And remember, hypoxia is low oxygen. So anemia, if you live in high altitude, or if you have any other hypoxic conditions that I talked about in the previous lecturette. Now, when you have chronic hypoxia, you don't have very much oxygen. You're breathless a lot. And so what this does is it triggers 2,3-BPG production. This is a protein. This production of this molecule in red blood cells. And in doing so, okay, it does the following. Look at this graph. You press pause. You read this graph and you tell me what 2,3-BPG does. Press pause. Press pause. Press pause. Press pause. Press pause. Don't just listen to the answer. Don't just listen to the answer. Okay, now, this is what it does. Look, it does a right shift. What do you folks know about right shifts? Decrease affinity. What do you know about decrease affinity of hemoglobin for oxygen? Releases in more oxygen for the tissues. Oh my God, we evolved this based on thousands and millions of years of being in a hypoxic state. This is what the red blood cells started doing. Amazing, okay? So anemia, like I said, ascent to high altitude. This is why a lot of fighters, when they train, or other athletes, if they really want to pump up their red blood cell production or increase the amount of oxygen released to their tissues, they go train at high altitudes. Not for a day, weeks, months, okay? Oh my God, 2,3-BG, 2,3-BG. Okay, let's wrap this lecture up. I got a little bit more to do. All right, we got to talk about carbon dioxide because this waste product is very important. Now, carbon dioxide is the hugest trigger for breathing, your breathing rate. Okay. How acidic your blood is. And so you folks already saw in the beaker slide that carbon dioxide is a little bit more soluble in an aqueous solution than oxygen. So 7% of it can just travel freely. Okay. So one way is dissolved, and you don't have to memorize these numbers. Okay. It's just a general sense so you can see the major avenues where carbon dioxide can be transported. Now, the second way is actually bound to hemoglobin. Can you imagine that? Thank you, hemoglobin, for not only carrying oxygen, but having the ability to also capture carbon dioxide. So some carbon dioxide can travel and get pinched by hemoglobin, and majority of it is via bicarbonate. Okay, so I want to show you folks. This is carbon dioxide. When you mix carbon dioxide and water together, and in the presence of this enzyme, you see this Ca? Ca stands for something called carbonic anhydrase. And what carbonic anhydrase does is allows you to make carbonic acid. Okay? And so the carbonic acid then can dissociate into this hydrogen ion, which, guess what? The hemoglobin can hold. Oh my God, hemoglobin. You go, hemoglobin. Thank you for not only capturing oxygen, capturing carbon dioxide, and capturing a little bit of acid. But then what we do with the bicarbonate is we go ahead and have it leave the cell. You don't have to worry about the chloride shift, but it leaves the red blood cell, and then we can just have this bicarb floating around in our bloodstream, 70% of it, right? And if we have too much acid in the blood, in hydrogen ions, then that buffer can go ahead and capture it to help us maintain our pH homeostasis. Oh my God, Becky's! That's amazing. All right. I want to close up this lecturette by just talking about integration. Is because what happens when there's so much information, we start to categorize it into little lumps or little lecturettes or however you're organizing your material. But it's really important to start integrating all this information together so that you can see what's happening on a system and organism level. So let's integrate, right? And the example that we're going to do is what's going on when in the alveoli I have a lot of carbon dioxide and I have low oxygen. So a couple things are happening, right? I have bronchioles and pulmonary arterioles. So I'm going to bronchodilate, but I'm also going to vasoconstrict. So I'm going to bronchodilate my bronchioles when I have high levels of carbon dioxide. And then that's going to allow me now to decrease resistance or increase flow. So I can now also increase ventilation and get that carbon dioxide out of the lungs. But in the arterioles, I'm going to constrict. I'm going to do the opposite. I'm going to vasoconstrict. And in doing so, right, I'm going to increase resistance, but that increase of resistance decreases blood flow to specific alveoli that don't have a lot of oxygen. So I decrease perfusion. That allows me to now not waste energy and don't divert blood where there's no oxygen to pick up. Okay, that's it, people, for this lecturette. You come back and we're going to do spirometry. All right.